Hello, everyone. Today's lesson is going to be fossil evidence of change. Fossil evidence of change. Um, the focus question will be, how can fossils provide evidence of past life? So we have people, generation that come before our generation. How can we use the fossils to measure, to know how long they lived or how long they've been a dead body? So this is what the question is asking. So these are the basic words we would look into in the process of this lesson. So a very common word which we use today is extinction. When we say an organism is gone into extinction, the meaning is all the species of the individual of the organism, they all died. Because as you know, we have a level of organization that starts from domain and ends in species. So when all of these individual species of an organism, when they die, we say the organism has gone into extinction. That is to say, they got wiped out. So, what about the Earth's early history? What are the things? What are the evidences? What are the things we saw that made us to know what happened in the past or the life that had gone before our own generation? The Earth formed about 4.6 billion years ago. So it's been recorded that the Earth formed about 4.6 billion years ago. So gravity pulled the densest. So force of gravity pulled the densest element to the center of the planet. So we have several layers. So, but the part of it which is most dense, so we have several layers. We have a we have the earth. So we have layers of rocks, of water, of different particles, different sizes, just floating around. So the force of gravity would pull things to the center. So this is the force of gravity pulling things to the center. So the force of gravity will pull the denser. The denser particles will be pulled to the center. So then this actually formed the dark part of the earth, which is called the core, the center. So after about 500 million years, then a solid crust is formed on the surface. So after almost 500 million years, we had a solid crust on the surface on this area, which is going to be this area. We had solid crust formed over the dense part of it. Then let's talk about the gases which were found on the Earth or in the atmosphere. So the gases that likely made up the atmosphere are those that were expelled by the volcanic eruption. If you've ever seen a volcanic eruption before, when it happens, it's gonna, let's say this is a mountain, then the mountain erupts. So when the mountain erupts, it's gonna give so many gases. So it's gonna release so many gases. So most of these gases which has been released, most of them are CO, carbon monoxide, or some of them are also CO2. We also have some of them be nitrogen. We have carbon monoxide. We have carbon dioxide too. So we have sulfur oxide. So we have hydrogen. So all of these gases are being produced from the volcanic eruption. Minerals is the oldest known rock. So minerals in the oldest known rocks when you find the rocks which is very old, so the minerals found in them suggest that the early atmosphere had little or no free oxygen. So because it is not possible for oxygen to thrive where we have all of these gases. So this is the reason why it's been understood based on the minerals which were found in the oldest rocks that the earth had no free oxygen in the beginning. So let's talk about the fossils now. Fossils are known to be any preserved evidence of an organism. Any preserved evidence. It might be the bones, it could be the flesh, it could be the skull, it could be some part of it. So once it is a part of an organism which has been preserved is called a fossil. 99% of the species that have ever lived are now extinct. 99% of the species that have ever lived before. So the meaning is the ones we have today, they are all new species. They're all new species. So it's been the organisms we have today, they are new organisms because almost only 1% of the one that lived before is remaining. And we still have so many organisms today which is not being identified. So, but only a small percent remain as fossil. Out of the 99% which is gone into extinction, just a very little percent is remaining as fossils. So that's the reason why we cannot really say categorically that we have evidences for every organisms that have ever lived before. So we have some, but we don't have everything. Most organisms decompose before they had a chance to become fossilized. What happens is when an organism dies, if it's not quickly been covered by sand and sediment, it's gonna decompose. And when it decomposes, that everything rots off or rots away, we would not be able to get fossil from it. So the only time we can get fossils is only when the organism dies and immediately we had what we had sediment forming over them. So this is when we say we have a fossil. So nearly all fossils are formed in sedimentary rocks. So when an organism dies, so the sediments will form over them. So this is why nearly all the fossils we have, they have been found in sedimentary rocks. So the sediments build up until they cover the organism's remains. So the sediments will build up over, let's say this is a dead insect, for example. So the sediments would build over it. So the first layer builds over it. The next layer comes and builds over it. The next layer comes and builds over it. So several layers will build over it. And it's going to remain underneath so many sediments. And before you know, it becomes a fossil. Sometimes the minerals which is in the rocks will fit themselves into the spaces in the bones and the muscles, so they replace the organic matter or fill the empty pore spaces of the organism. Or the organism decomposes and is going to leave behind an impression of itself on the rocks or on the surfaces where they actually laid. Scientists who study fossils, we call them paleontologists. So they are the ones who find bones around and find every evidence of an organism that once lived before. Relative dating is a method which has been used to determine the age of rocks by comparing them to those in other layers. So relative dating, as the name implies, relative to something. When we talk about relative, that is to say you're comparing something with another thing. So that's what we call relative to something. So it's actually a method of determining the ages of the rocks by comparing them with the layers of other rocks. So this is an example of how fossils are formed. So let's say these are fossils formed in this layer. This is another layer. So we've got layers A, B, C, D, E, and F. Relative dating is based on the law of superposition. What does superposition mean? It says that the younger layers of rocks are deposited on top of the older layers. So that is to say, organisms in layer A are younger than organisms in layer B. Organisms in layer C are younger than organisms in layer D. The youngest organisms are found here, and the oldest organisms are found here. So this is the law of superposition. So the law states that the younger layers of rock are deposited on top of the older layers. Now let's talk about radiometric dating. Radiometric dating uses the decay of radioactive isotopes to measure the age of rocks. An isotope happens when you have two elements of the same atomic number, but different mass number. So when you have when you have carbon-12, we have carbon-13, we also have carbon-14. So all of these three carbons, they are isotopes of each other. We also have isotopes. So I don't need to go deep into isotopes because it's not basically part of the things I'm supposed to talk about much. But isotopes is usually happen where you have two or more elements or two or more atoms that have the same atomic number but different mass number. Radiometric dating depends on knowing the half-life. The half-life is the time it takes for half of the original isotope to decay, time that it takes the half of the original isotope to decay. Now, this is the percentage of carbon-14 that remains. So let's take a look. We have 100% full at 0 year. Then in around 1845, so what happens is, this is the ages. So we got a drop of 20%. So then when do we have half-life of this carbon-14? You're gonna go to 50 here. So you're gonna trace the 50 to this place. So it's around 5,730. So the half-life of carbon-14 is 5,730. That is to say, it takes 5,730 years for half of carbon-14 to be broken down. So the meaning is 50% of carbon-14 is being broken down within 5,730 years. The meaning is the half of the 50% will be broken down in the next 5,730 years. So the meaning is 5,730 times 2, which is going to give you 0,646,411. So in 11,460 years, half of the 50% will be broken down. That is to say, half of what is remaining will be broken down. So this is another half-life. So then in another one, in another half-life, this will be this is how long it takes for 1/4 of the carbon-14 to be broken down. So what am I trying to say is this. If it takes 5,730 for half of carbon-14 to break down, so automatically these multiplied by 2, multiplied by 1/2, which is going to be 1/4. So 1/4, which is how we got that from 1/2 squared, which is going to be 1/2 times 1/2, is going to take the same one, is going to take 11,460 years for 1/4 of carbon-14 to be broken down. So I think we understand. So we're going to calculate by half, not by the original. So this is exactly what we need to understand. So you can check it properly. If you want to ask more questions about that, you can leave questions about that in the comment section. So the next one is the geological time scale. So the geological time scale is a model that expresses the major geological and biological event in the Earth's history. Epochs are the smallest units of geological